joint work with my former PhD advisor, Pablo, but there's also parts that are joint with Russ Drake, who's a roboticist at MIT, and his PhD student, Ani Majumdar. So the setting for today is pretty simple. I'm going to look at the differential equations that are given by polynomials. So x dot equals f of x, where f is a mapping from Rn to Rn. Each entry of it is a multivariate polynomial. So here's an example. And this little dot notation is the derivative with respect to time. So in this example, so this mapping defines a vector field. So at any point x, you get a little arrow. And then the solution of the differential equation, which from different initial conditions, which are these blue trajectories, are trajectories that satisfy this differential equation with respect to time. Okay. So in general, for nonlinear differential equations, it's very difficult to write down explicit formulas for the solutions. But typically, we're interested in some sort of qualitative properties of the trajectories as a whole. So what are some examples? So for instance, we may be interested in establishing stability of an equilibrium point, which means that if you have an equilibrium point is just a zero of f, is a point where if you start there, you don't move. And stability simply means that is it true that in a neighborhood around the equilibrium point, all trajectories flow to the equilibrium point. Or you may be interested in boundedness. Is it true that all trajectories remain bounded? They don't shoot off to infinity and so on. And of course, this sort of a tautology to talk about applications of dynamical systems. So everything that moves is a dynamical system. But sort of many of these properties are relevant in different applications. For instance, if you're modeling spread of epidemics or spread of diseases, then you want to know whether the number of sick people remains bounded, for instance, given a reasonable model of this. Or if you're modeling dynamics of prices of some commodities in economics, then stability is relevant. You want to know whether deviations from an equilibrium price would tend back to the equilibrium price or whether it would move away from it. So for this talk, my focus is on the stability. So let me define it a little bit more formally. There's two notions, local asymptotic stability and global asymptotic stability. So these are properties of an equilibrium point, which means a point where f is 0. And just roughly speaking, local asymptotic stability means there is a neighborhood around the point where all trajectories go to the equilibrium point. And global means that for all initial conditions in Rn, all trajectories flow to the equilibrium point. So in this picture, it looks like this is globally stable. So on the decision problem is, given a representation like this, given these coefficients and an equilibrium point, tell me if it's stable or not. So what does this have to do with optimization? So in terms of many questions of this form about dynamical systems, whether about stability or boundedness and so on, can be turned into questions about searching for functions that have certain properties, like non-negativity or non-negativity on regions or convexity. And this is because of a whole class of theorems, which generally I call Lyapunov theorems. But the most basic one, which many of you, I'm sure, have seen, but let me just repeat it because I'm going to use it, is Lyapunov stability theorem. So this says that suppose you have a vector field, and sort of in the simplest case, suppose you want to prove that the origin, which let's say f of 0 is 0, is globally asymptotically stable. So this theorem tells you that if you find a function v, which is positive everywhere, it only vanishes at 0, so it's a mapping from the state space to R, and then v its derivative with respect to time is negative everywhere. So what is this v dot? So imagine a trajectory moving in Rn, and you evaluate this function v on the trajectory, right? So for every point, this gives a positive value, and as you move along the trajectory, this value should monotonically decrease. So this would give you a proof of global stability because it's sort of obvious. It says no matter what the trajectory is doing, you have this energy function which is monotonically decreasing. So eventually we should go to 0, which means that the state x must go to 0. Okay, so that's how the theorem works. What's nice about it is that we don't need access to the solution, to the trajectories to reason about this, because v dot is simply by chain rule is the gradient of v inner product with f, which f we already have, right? So it's very nice. If you find the Lyapunov function, I don't know what happened. Okay, you have stability, but then the obvious question is there always such a function? There are classical theorems in controls that tell you there is, in fact, always such a function. There is, in fact, the continuously differentiable Lyapunov function for any stable system. But then the whole business is to find one. Okay. Since I'm talking about polynomial vector fields, it's kind of natural to look for Lyapunov functions that are polynomial functions themselves. And it should be sort of obvious to this crowd that this has become more popular because of sum of squares techniques. And this is an idea that goes back to the thesis of Pablo in 2000, the idea of sum of squares Lyapunov functions. Is it because of my computer? Okay, let's hope it doesn't happen again. So what's the idea? We're going to look for a V which is polynomial. And moreover, instead of requiring these positivity conditions, we're going to require V to be a sum of squares and minus V dot to be a sum of squares. So minus V dot is just another scalar valued polynomial. Remember, is this polynomial, right? And this condition is linear in the coefficients of V. So it should be obvious to many of you that the search for this V is a semi-definite program. And that's why this is nice and powerful. Just to make it more concrete, let me give you a quick example. Suppose someone gives you this vector field in R2. So this is just one trajectory, this black curve is this crazy thing. And we want to prove that all trajectories flow to the origin. Well, you go to your semi-definite programming solver. You look for a Lyapunov function of, say, degree 2. Oh, OK. What can we do? Huh? Oh, when I get close, that happens? Okay. Okay. So, and typically you fix a degree, look for a Lyapunov function of some degree. If you don't find one, you go to higher degree. So in this particular example, Mary is the what? Or maybe let me just unplug it because I have battery.
No, maybe you don't put it when you walk.
Oh, I see. That makes more sense. Okay. Thank you. So in this case, you have to go all the way up to degree 8. But when you do so, the STP solver just outputs a degree 8 Lyapunov function. You have a proof of stability. So these curves are sub-level sets of this degree 8 polynomial, which are invariant for the trajectories. So a natural question, for instance, here is it, in this case, why did I not find one of degree 4 or one of degree 6? Is it because this sum of squares condition is too strong, or is it that really there wasn't one? So I think if Bernd was giving the talk, he would ask as a pop quiz this question, but if anyone wants to take a guess, I'll get back to it later. Okay, so this is the type of questions I want to argue in this talk. Is it true that the converse of these implications are true or not? So that would be the core of the talk. But before I do that, I have just 2 slides on a cool application of this in robotics, which is something I did with Ross and Ani. So it turns out you can use these ideas to search for Lyapunov functions and controllers that stabilize mechanical systems. So here is an example. It's called the acrobat. So is a pendulum with 2 legs, and this is what it looks like. It's sort of hard to see when it's hanging down in this position. And your control can only be applied to the joint in the middle, not to the joint on the top. And the task is to swing this up and then stabilize it back up there. Okay. So the reason why it's called an acrobat, because it's an analogy with this acrobatic maneuvers, that these people have to create momentum just from their hips with no momentum from the hand, and go up and stabilize themselves. That's why the torque is only applied here and not on top. So let me just show you a movie that does this. So these controllers have been found with SOS techniques. It's very hard to see because of the light, but okay, thank you. So this goes up and tries to stabilize. So I'm hiding a lot of details here, but this is a dynamical system where X, in this case, would have 4 states, sort of the angle of these pendulums with the vertical line and their derivatives. And this is what you get. So here it is the case where we're doing local analysis, so it's a little bit different from the global scenario that I told you. But sort of what these pictures are on the bottom are when you're back on top. So this is an unstable equilibrium because any deviation from it would make you fall. These are bases of attraction. So there's a controller designed so that if you deviate, you come back to the stable position. And the red is the size of that basin when you use SOS techniques, and the blue is when you use more classical control techniques called linear quadratic control. And you see we can prove much bigger regions. So this is a four-state system. These are projections in different spaces. So this is theta 1, theta 2. This is theta 1, theta 2 dot. Okay.
What are the standard techniques?
The standard techniques sort of linearize the dynamics. They look for a... So they solve a Lyapunov equation, essentially. They don't solve STP. So here I have to say the controller which gives you the red is a cubic controller in the state. So with classical techniques, usually they give you a linear controller. Here we're doing higher order polynomials. The picture on the top is for the swing up task. So again, so here is a little bit more complicated because you don't have an equilibrium point that you want to stabilize. You have a whole trajectory that you want to make sure deviations from this trajectory take you back to the trajectory. So again, the red is the basin we can prove. So there's a nominal trajectory that takes you up. The red tells you how much deviation you can handle and still be brought back to the trajectory. And this is verified by sum of squares inequalities. Okay. So now back to the more basic. So again, I'm studying global asymptotic stability because it's just cleaner and simpler, but in applications, usually the local version is more interesting. Okay, thank you. So the obvious question here is that, if you have a system which is globally asymptotically stable, we know there is always a Lyapunov function, but is it true that there is always one that is polynomial? Okay, and suppose there is one, is it true that there is also always one that satisfies these two sum of squares conditions, right? A closely related question is that, what is even just the computational complexity of testing stability? And this, of course, is related to what sort of Lyapunov functions you expect to have, right? And so one comment I want to make is that pretty much the only well-understood case is the case of linear systems. So if the degree of f is 1, when you can always represent your system like this as a matrix times x, then stability is very well understood here. I mean, a linear system is stable if and only if there's a quadratic Lyapunov function. So you always have degree 2 Lyapunov function in this case. This condition is sort of easy to check, polynomial time, and everything is good. As soon as the degree is 2 of the vector field, then a lot less is known. And we've made some contributions to that question. Okay, thank you. So just I'm going to say a word on the complexity, but won't dwell on it that much. So there's a well-known conjecture of Arnold from '76 that says the stability question is undecidable, meaning there shouldn't be any algorithm that terminates in finite time. It's still open, and sort of just to show you that it's related to this Lyapunov questions, is that suppose it was true that there is always a polynomial Lyapunov function, and suppose you could compute the upper bound on this on the degree of such a Lyapunov function, then the question would become decidable. Because one by one, you could check in finite time whether there is a polynomial that satisfies certain inequalities, right? I really don't know why. Thank you. So a result that we have is a weaker result than undecidability. We've shown that at least the problem is NP-hard already when you have cubic vector fields. So this rules out polynomial time algorithms. For those of you who are going to ICC up next week, I'm giving a related talk, and I present the proof of this. Okay, I have to go quick before it's done. Okay, this is a slide I just wanted to advertise that, for many of the properties I had on my original slide, we have 10 of them. These are all yes/no questions that we've shown all are NP-hard. There's a reduction from 3 sat to all of these, and the statement that these are hard for the degrees that you saw. The degrees, if the degree is 3, or these degrees, then these decision questions are hard to decide. Okay, so now back to these 2 questions. So we have sort of these partial answers to these questions. There's a concrete counterexample that I'm going to present to you on the next slide, which says it's not true that there is always a polynomial Lyapunov function for stable polynomial vector fields. And here the answer is sort of twofold. One is that if you have a polynomial Lyapunov function and you want one that satisfies the sum of squares conditions, If you insist that that is of the same degree as the red one, then the answer is no. But if you allow the degree to be higher, then under two assumptions, we can prove the answer is yes. One is that if the vector field is homogeneous, meaning all monomials in F have the same degree, and the other is that if the vector field is on the plane, so you have only two state variables. And the remaining cases is still open. Okay. So let me present to you this counterexample, which is very nice and simple. I like this example a lot. It's joint work with Miroslav Krisic and Pablo. So this is a vector field in R2, which is just slightly nonlinear. The only nonlinearity is this xy. The claim is this is globally stable, but there is no polynomial Lyapunov function of any degree. Okay. So proof of claim 1. So how do you prove something is globally stable? You do it with the Lyapunov function. Instead, we cannot use polynomial Lyapunov functions here. It turns out there is one which uses logarithm. So if you take v equals this function, then this is obviously positive definite. If you look at v dot, it's some rational function. You can, for instance, use sum of squares to show that it's negative definite. I should have used your laptop. My fault. Yes. Okay. Okay. So the more interesting claim is that there is no polynomial Lyapunov function. So why is this so? And I claim that just by looking at these trajectories in the non-negative orthant, you can argue this. So if you look here, this is one of the few cases where the dynamics is simple enough where we can actually explicitly write down the solution, right? So the solution of y dot equals minus y is just e to the minus t. So the y coordinate, no matter where you start, independent of x, just shoots down to 0 exponentially fast with time. But if you look here, there's a transition on the line y equals to 1. So sort of x moves out till y hits the line y equal to 1, and then immediately comes back after y is equal to 1. And you can see that here, because if y is more than 1, then x dot is positive, meaning x is increasing. And if y is less than 1, x dot is negative, you go back down. So essentially, there's a double exponential term here. And the idea is that before y has time to hit the line equal to 1, x is moving double exponentially fast to the right. And so it has faster growth rate than any polynomial can hope to decrease. So what is the idea? So suppose there was a polynomial Lyapunov function. Then it better be that the value of that polynomial here is larger than the value here, because Lyapunov functions decrease on trajectories, right? But so to make this formal, you can take a line. So let's pick some alpha. Let's say alpha equal to 2, and look at the line of initial conditions of, let's say, k, 2k, and look at the crossing with the line y equal to alpha for some alpha. And you can show that the crossing is e to the alpha k alpha. So if there was a Lyapunov function, this inequality should hold, that where you start, you should be larger than when you end. But this is impossible to hold, because if v is a polynomial, the left-hand side is growing exponentially, the right-hand side is growing polynomial. So once you fix any degree, you can go high enough in this line such that you increase much faster than that polynomial. So that's the idea. I have to say that after we publish this, there's an independent and very nice example of Bacciotti and Rossier, which also gives a counterexample to existence of polynomial Lyapunov functions. Is very different in nature. It relies on the fact that some coefficients in their vector field is irrational, and that's the idea of their proof. So in that sense, it's a little bit more application-oriented, because if you do anything on a computer, you won't have irrational. Yes, question?
But you now prove this more general, because you don't need that the exponents of your Lyapunov functions or the powers are integer, right? Can be any fractional number too.
Yes, but because powers of Lyapunov functions are Lyapunov functions, so if you had like something to the power 1/3, you could raise it and get a polynomial. So that immediately rules that out. That's correct. But there is a more. I'm sorry?
You can have even square root of pi at the exponent.
So does that rule? Yes, because the growth rate would still hold. That's true. That's a good point, actually, because this other one does not rule that out. Actually, it does this one too. This rules out any analytic function.
And I think this is a very singular counterexample, because I classified all these flows. These are Lotka-Volterra equations, all possible. 109 different phase diagrams. And only in very singular cases you get this behavior.
It's not singular in the sense that it's robust in the population.
Yes.
You perturb this assembly.
Yeah. So
But
that's
there's a different way of singularity. Yes. Okay. But the majority of the cases have a very nice Lyapunov function, which are powered, which basically are monomials.
our monomial.
Monomials.
Okay.
But with irrational coefficients. The coefficients are basically the coordinates of the fixed point, which is here 0. This does not apply, but you have to shift it somehow to different phases.
So I agree with you that this also rules out not only rational powers but irrational powers, but I think the other one rules the other counterexample rules out also. So the point that Pablo was raising is that you completely killed
In
it.
the vector field would not matter. That's what he said, right?
So yeah, perturbation. This is robust to perturbations, whereas the other example is not. So that's also
Design a controller.
yes.
No.
If you guys don't mind, I'm going to continue talking before this dies.
That thing was fluxed. Sorry.
Oh, now it's fixed?
Yeah.
Okay, thank you.
Thank you, Pablo.
The second time I tell you thank you. Okay, so now to this question. So suppose now you're on a special case when there is a polynomial Lyapunov function. Can you also argue that there is one which is a sum of squares? And you may tell me, why we already know there are non-negative polynomials that are not sums of squares, all the way from Hilbert. Why doesn't this answer this question? And this is slightly different because Lyapunov functions are not unique, right? So it could happen that there is a vector field which has a Lyapunov function which is non-negative but not a sum of squares, but it also has another one which is a sum of squares. So to answer the one that the answer is no, you have to give a vector field which is stable, and even though it has a polynomial, it has no polynomial which satisfies these two conditions, and that's exactly what this next counterexample does. So is it so it's a vector field in R2, and the statement is that no quadratic Lyapunov function, there is no value of C1, C2, C3, which would satisfy these two SOS conditions. We can switch quickly to your laptop, but I think I'm mostly done. I'm sorry?
Just go
Okay. So the first part of the proof that there is no quadratic that satisfies this, you just have to show some SDP is infeasible because that search is a semi-definite program. Okay, and then the second part is that there is in fact a Lyapunov function if this is a valid Lyapunov function which sum of squares doesn't find. And the reason, obviously this is a sum of squares, but what fails is the V dot condition. In this case, V dot is something like the Motzkin polynomial. So that's the idea why this fails. Okay, and then what was nice is that, even though sum of squares doesn't find a Lyapunov function of degree 2, if you crank the degree up to 4, it does find one. So, and there's no reason why we should look at quadratics, right? So in this example, you find a quartic. So then there's a natural question, is this always true? That if you keep increasing the degree, you would always find one? And this is the next two theorems, which says that under two conditions, this is true. So the statements are exactly the same in these two theorems. The assumption is different. So the statement is if there is a polynomial one, then there is also one that satisfies the sum of squares. The assumption in the first one is that the vector field is homogeneous. The second one assumes that the vector field is in two variables. Okay. Just a word on this proof. These proofs are super simple, and they're almost trivial, and they depend on some very nice results of Claus, which are these two theorems. The theorem says that if you have any two positive definite forms P and Q, there's an integer k such that P times Q to the k is the sum of squares. The second theorem is exactly the same, except that you have now restricted to 3 variables, but you allow one of the two forms to have zeros. So Q must be positive definite, but P can have zeros, positive semi-definite. Still the same implication is true. So essentially, by using this theorem, our W Lyapunov function will simply be V to the k for some high enough k. And as you see, this involves some products. So these products appear in the V dot condition, and we can guarantee that minus V dot is also a sum of squares by using this. And the reason why this is in 2 variables is that we need to homogenize and then dehomogenize. That's where we can use this 3-variable theorem. So that's the idea. And again, I completely agree. This is very restricted, the homogeneity, and planarity assumption. It would be very interesting to prove it in general, if it's true. Just my last two slides, I want to say a word on homogeneous vector fields. So this again where every monomial in F has the same degree. So we prove this implication is true. This we conjecture is true, and I don't think it would be that difficult to prove, and it would be very interesting because it would give you the whole thing. So the reason why this should be true is that for homogeneous vector fields, because they scale, is enough to look at them on the sphere. So we know there is a classical continuous Lyapunov function. You just have to approximate it with polynomials on the sphere and still meet both inequalities on V and V dot. So that's a conjecture, but what the next result proves is that even if this conjecture is true, which again I believe is true, you cannot bound the degree of such a Lyapunov function. Okay, this is what the next result says. So this is an example in two variables of a cubic vector field. So this theta and lambda are just parameters. Once you fix them, you get a cubic vector field in x and y. And the statement is that for any degree of a candidate Lyapunov function, let's say 1,000,000, there's values of theta and lambda that you can pick such that this system is globally stable, but there's no Lyapunov function of degree 1,000,000. In particular, you can take any rational number, take lambda to be, let's say, pi to k decimal digits, and theta to be this. So just what's the intuition behind this? So and this is based on the result of Bacciotti and Rosia, it uses the same idea. If theta is 0, essentially you get a dynamical system that precisely moves on this curve, which is this non-algebraic curve. And by changing theta, this is a rotation matrix. Essentially, I'm moving the dynamics inside, going to 0. And as theta goes to 0, I get closer and closer to this curve. So my polynomial would need to approximate this curve better and better. But because it's not algebraic, the degree has to blow up. You have a question?
Why can't you do the trick of adding a variable to homogenize the polynomial, and then that variable is just constant? So why can't you
To homogenize the vector field?
to homogenize the polynomial? I mean,
So
set it equal to 1, and then
no, that preserves non-negativity, for instance. But if you're talking about homogenizing the vector field, that does not preserve stability, for instance. Okay. I mean, for one thing, it doesn't preserve existence because here, okay, at least if you believe this conjecture, then that would immediately give you a contradiction, right? Because I had an example which had no polynomial Lyapunov function. So if your homogenization should not even preserve existence of polynomial Lyapunov functions or stability. I've thought about it. So it doesn't preserve stability for one thing. Okay? And you have to define what the dynamics in the new variable is. But so it's not 0, right? So it says constant. So that wouldn't preserve stability. Okay, and then the last one slide result. This is like a little cute result. I like this. And it says that there is no monotonicity in the degree of Lyapunov function. So what people usually do, they look for a degree 2 Lyapunov function. If they don't find one, they go to degree 4. They go to degree 6. So what this shows is that this is not always true. So it's an example of a vector field where there is a degree 4 Lyapunov function, but not of degree 6. And the Lyapunov function is this TV screen, and essentially this is hard to approximate well enough with a degree 6 polynomial. So that's why this monotonicity fails. So thanks for bearing with this screen. Just to recap, I talk about polynomial differential equations. They have many applications, and these techniques based on sum of squares and semi-definite programming are quite powerful. Then I gave you a summary of some results. So I sort of just advertised this result that is NP hard to check stability. It could even be much harder. It could even be undecidable. I showed that there is no polynomial Lyapunov functions, but if there is one, if you increase the degree under 2 assumptions, you find the sum of squares. But for the same degree, you cannot opt for that. So I'll stop here. Thank you.
Question. In the case where you find possibly rational square of rational functions,
rational Lyapunov functions that are rational functions.
Yeah.
So our example rules that out also.
Have you tried that? Or?
So the counterexample I had with 2 variables, that also has no rational Lyapunov functions.
In the case where
and the one of Bacciotti and Rosia actually has no analytic Lyapunov functions.
But in the case, for example, where there exists an SOS, you have no
For the second counterexample.
yeah, no, but for the example where there exists an SOS,
Uh-huh.
and you find simpler rational function, would it be?
Oh, lower degree, you mean?
Yeah.
That's totally possible, I think. The problem is that the search for a rational Lyapunov function is not an STP unless you fix the denominator or
Fix the
something.
denominator.
Yeah. But it is possible that, let's say for one of my ugly examples when I needed degree 8, actually let me just, for the fun of it, let me go back to the pub quiz. So in this example, that this has no Lyapunov function of degree 2, 4, and 6, it could be possible that it could have a ratio of 2 quadratics. Doubtful, but so does anyone want to guess, does this really have a degree 2, 4, 6 Lyapunov function, or is it because sum of squares is too strong?
What happens if you depart from the assumption that the vector field is polynomial? I mean, you can always multiply by a transcendental function which is strictly positive.
Yeah, and that would preserve the
same trajectory. You have a
same
time
trajectory of the rescaling. So the techniques still apply, right? I mean, so for rational, let's say each vector field each entry is a rational function. People use actually that's applied a lot. People look for polynomial
The
functions.
denominator is nice.
So if yes, no poles. Or
No poles. Exactly, but then it's just equivalent to.
you
the
can clear
trajectory
denominators.
is the same.
Yes, you can clear denominators by a product of denominators. Because that preserves the math.
On the other hand, the globalus or the stability assumptions are quite rare, quite hard to satisfy. You can go even 3 dimensions and cubic right-hand sides, and you end up with Lorentz attractors or
Yes, of course.
chaotic behavior. So it's very difficult to go back. To go forward, it's nice, but
To go back, you mean?
I mean, you want to have a Lyapunov function and you don't find the polynomial or you don't find the SOS, you cannot be sure that your
system is stable or not?
yes.
Well, yes, that's what this shows. But there is always a C1 Lyapunov function. There is always, if your system is stable, there's. Yeah.
If the system is stable.
Yeah, but chaos is exactly the reason why this could be undecidable, right? I mean, at least it shows the problem.
Other questions? I have a question. I mean, the question
Now
about
that we stop, this never flipped.
That's okay.
it got him. Why did Arnold think it is undecidable? Why I mean, what was the
Okay, so why did he think so? For one thing, so Arnold has this result that says that it is a parametric differential equation in, let's say, 3 variables, degree 5, I don't know, and says that the set of coefficients for which this is stable is not a semi-algebraic set. So that's already very strong evidence of difficulty and undecidability.
But semi-algebraic is still, I mean, questions about semi-algebraic sets are still decidable.
Yes, he showed is not semi-algebraic.
It's not
Yes.
semi-algebraic.
So even in fixed dimension and degree, the set of coefficients is a fixed vector field in 3 variables degree 5 with like a couple of coefficients are not fixed, and the set of coefficients for which the origin is asymptotically stable is not semi-algebraic. So that's the result of Arnold. That suggests undecidability, and another reason is that no one has a finite time algorithm.
On the other hand,
I mean, I guess the other reason is that, a dynamical system can simulate arbitrary computation. I mean, something that's the insight, if you want.
Okay.
If you can do arbitrary computation, it should be.
okay. Then,
And there are, much after Arnold, but right now there are many examples of dynamical system questions which are known to be undecidable. They're usually in discrete time, though, which is simpler to show. So the difficulty really is that these are continuous time, and this makes it harder to prove. But, yeah.
there are no other questions. Let's thank the speaker again.
Thank you.